Our speaker tonight, Camilla Benbow, made her mark early with a 1980 science paper entitled Sex Differences in Mathematical Ability, Fact or Artifact. The second author was her major professor, Julian Stanley, well known for his work with mathematically gifted children at Johns Hopkins, where Dr. Benbow received all her degrees in psychology and in the education of the gifted. She's gone on to write numerous papers on the gifted and has received many recognitions. She joined Iowa State in 1985 and is now in her first year as chair of the psychology department. Also, she somehow has managed to have 7 children. Tonight, she will address us on the math-science pipeline. Can it meet tomorrow's technological needs?
Well, thank you. I'm honored to be here today to give the Sigma Psi Honor Lecture, and I guess I especially appreciate being invited here to give this lecture, given the topic of the previous lecture that was given by Sheila Tobias. For those of you who were here at Sheila's talk last spring, you might have remembered that she was arguing that the sciences lose or discourage many bright students from entering them due to the way we teach in the sciences. And Sheila was arguing, for example, that the problem-solving focus that is found to be distasteful to students who are more verbally oriented and who wanted to see the big picture. When I was listening to her talk, her descriptions of the way we teach and the different ways we teach on the 2 sides of the campuses, say, for example, physics versus English, it reminded me of the 2 worlds of C.P. Snow. Now, Sheila suggested that the sciences change to attract the bright students who now steer away from them. Or that is, that the sciences try to attract the other world of C.P. Snow. Now, my reaction at that time was probably very similar to that of C.P. Snow's, and that is, we probably can't do that so readily. Environments such as the physical sciences require certain skills and are attractive to certain types of people. Also, certain people see the big picture in very different ways. And also, the big picture in different disciplines can be perceived through different symbols. And when I was thinking about it and what her lecture, I kind of felt like asking the sciences to significantly change the way they teach and to try to accommodate more verbally talented students through changing the way they teach is sort of like asking nursing to become less social so they can attract more introverted people. Now you might be wondering, why am I carrying on about all of this? Well, I'm making these remarks because they provide a nice backdrop to my talk today. And I also thought it probably would spark your interest in what I have to say. But be assured that I'm under no illusion that all of you guys will agree with me. My work, for the most part, has been politically incorrect, as some of you may already know, and the rest of you will probably find out today. And the reason that my work has been perhaps politically incorrect is that there are a lot of gender differences in the variables that predict participation in the sciences. Well, now on to my talk. Since 1977, I have worked with mathematically talented students through the study of mathematically precocious youth, which I now co-direct with my colleague, David Lubinsky. SMPY, as we call it, is located in the Office of Pre-Collegiate Programs for Talented and Gifted at ISU, and at this office I co-direct with another colleague, Lynn Glass. And some of you may be aware of OPTAG and the various programs that we conduct, and you'll hear a little bit about them throughout my talk today. But anyway, SMPY was founded in 1971 at Johns Hopkins University by my graduate advisor, Julian C. Stanley. A story, perhaps first told by Mark Twain, captures the essence of SMPY's work with mathematically talented students and our concern with alleviating the loss of this human resource. It also depicts a long-term outcome that our work is designed to circumvent. Well, what is this story by Mark Twain? Well, it's about a man who sought the greatest general who had ever lived. Upon inquiring as to where this individual might be found, he was told that the person he sought had gone to heaven. At the pearly gates, he informed St. Peter of the purpose of his quest, whereupon St. Peter pointed to a soul nearby. "But that," protested the inquirer, "isn't the greatest general of all times. I knew that person when he lived on earth, and he was only a cobbler." "I know that," replied St. Peter, "but if he had been a general, he would have been the greatest of them all." When working with mathematically talented students, we attempt to find and even provide environments where their talents can best blossom and come to full fruition. What these environments consist of and learning how to provide them is the goal of our research. Now, SMPY was first interested in identifying adolescents who possess exceptional intellectual abilities, and then to ascertain the factors that contribute to their optimal educational and vocational development. To identify mathematically talented students, Stanley devised the concept of a talent search. Now, what is a talent search? Well, a talent search invites students who are in the 7th and 8th grade, who are already known to be gifted, that is, they've already scored in the top 3% on standardized achievement tests like the Iowa Test of Basic Skills. We invite them to participate, and we ask them to take the College Board Scholastic Aptitude Test, the test that people on the East and the West Coast tend to take before they go off to college, the SAT. That is, to these 7th and 8th graders, we administer a test designed for above-average 11th and 12th graders. The SAT has an SAT math part and an SAT verbal. The SAT math measures mathematical reasoning ability, and the SAT verbal reasoning ability. Well, when we give that test, that SAT, to students who are 4 to 5 years too young, supposedly, to take that test, they generate score distributions that are very similar to high school students. Now, you may be sitting there wondering, well, what do these scores mean? Here you have a 7th and 8th grader who can earn the same score as a 12th grader, but what does that score mean? If I could have my first slide. So what we try to do is to figure out what is the predictive validity or the utility of these test scores. And here in this slide, what we did was that we took students that we knew were all in the top 1% in intellectual ability, and we put them into two groups, the top quartile of the top 1% and a set of individuals who were in the bottom quartile of the top 1%. They were all in the top 1%, but one was in the top and one was in the bottom quartile. We then looked at their academic achievement and accomplishments over 10 years, from age 13 through 23. And we wanted to ask the question, is there differences in achievement between those in the top and the bottom quartile? And as you can see by looking at this slide here, there were indeed very large differences in these two groups. And you can see there's a D and there's an H, but if you look at that D statistic, what that D refers to is, for example, like a standard deviation. So the D of 1.24 is that the difference is equals to 1.24 standard deviations. And so you can look and see how large those differences are. But the average effect size, the average difference between the top quartile and the bottom quartile of the top 1% was 0.65 standard deviations. Quite a difference. Now, a lot of people believe that after a certain point, intellectual ability doesn't make a difference. Other factors come into play. Clearly what this demonstrates here is more is better. And clearly what it demonstrates is that these scores that we obtain for these 7th and 8th graders do have meaning. They do predict eventual academic achievement. Anyway, when we administer the SAT, if I could have I have my little thing here, don't I? What happens when we administer the SAT to these 7th graders is that we are now able to spread out the talent. And if you look here, before we give the test, we have students who are all at top 3% in ability, and you cannot differentiate those students. But when you give them the much more difficult SAT, you have students who score all the way from chance to the top score possible. And what some people may not realize when you look at this thing here is, like, when you look at the IQ distribution, if you look at the distribution of IQs above, say, 130, that's the 1/3 of the range of IQs that you can get. And that clearly shows itself right here in that picture. Now this has very good use for us because we tend to work with extremely able students. And when we can separate the top 3% out like that, we can see who's able and who's extremely able. Today, the talent search concept that Julian Stanley began in 1972 has almost 150,000 kids participating in it on an annual basis. We have tested well over 1 million kids to date. And every single state in the nation has a talent search. And even we do here in Iowa. And here at ISU, we conduct the Iowa Talent Search, which has about 5,000 kids participating in it on an annual basis. Now, we work with these students that we identify, especially the able students, to try to discover what are the best ways to educate them. In the process, we've tried various interventions. The very first intervention that we worked with was a fast-paced mathematics class that we began in 1972. And in that fast-paced mathematics class, we had about 30 kids go through the entire pre-calculus curriculum, that is 4.5 years of math, in 14 months. We did that again in 1973. Well, when we were doing that, we thought that was pretty great, but after a while we thought we could do even better than that. So we changed our procedures and tried a new approach to teaching math. And in 1978, we could teach 4.5 years of mathematics to these very bright kids in 6 weeks. And nowadays, what we do here, for example, at ISU, we teach 1 to 2 years of mathematics in 3 weeks to our students. We've always also done the same for the sciences. We can teach a whole year of high school physics, a whole year of chemistry, or a whole year of biology in 3 weeks, including lots of time in the lab. Actually, our way we teach is through the lab. And when we administered, for example, College Board Achievement tests at the end of those 3 weeks, the average score of the students in those classes is well over 700. So they clearly have mastered the content. Now, some of you might be sitting back there and say, I find that very hard to believe. How can anybody learn high school physics in 3 weeks? What I say is, what that points to is how inappropriate the regular curriculum is for these kids in the schools, because we have demonstrated this over and over and over again. And it tells us what these kids can do if they're given the opportunity. And the refinements of these types of courses that we've been working with have now really become standardized applied interventions. And we do offer them here at ISU through the SciTech program or the Explorations program. And in the summer, we have about 400 kids here on the ISU campus participating in these kinds of courses. And so if you've been on campus in the summer and you start thinking, what's going on with me? Are these students getting younger? They are getting younger. They actually are younger. We have a big population and we fill up the dorms. Anyway, and some of you may even have seen some of these kids here on during the academic year. We have some of our kids come here in the academic year. We have, for example, a pair of twin boys who last year at age 15, took sophomore physics and differential equations and did very well. Some of you might have read about them in the papers. They're back here at ISU again this year taking some more courses. By the way, those kids had scored 700 on the SAT math before they turned 11. Those are the kinds of kids we work with, and not always so able as that. Anyway, that is kind of the program's part of our work, but an important part of what we're doing is that we're conducting a 50-year longitudinal study. And this study has now completed its 20th year. Now let me just take some time to describe what this longitudinal study is like, because the data that I'm going to present to you at the end of my talk comes from this longitudinal study. In the longitudinal study, we have 4 cohorts of individuals. We have our first cohort of individuals who were identified in the early 1970s, and this is how we identified them, and their ability level is about the top 1%. Our second cohort was identified in the late 1970s, and they represent the top 0.5% in ability. Our cohort 3 was identified in the early 1980s and represents the top 1 in 10,000 of their age group. And our cohort 4 is a new and ever-growing cohort, which now actually has about 1,000 kids in it, and they too represent the top 5% in ability. Cohort 4 are the Iowa students who are participating in our SciTech programs. We also have a 5th cohort of students, and these are individuals who are graduate students in this nation's top math science departments. We're doing a retrospective study of these individuals. I'll talk a little bit more about them later, but they're there for generalizability. How well do our findings from these cohorts generalize to another group of students who must be gifted as well? There are some nice features of the way we set up the longitudinal study. Each cohort is separated by a few years. Each cohort is being surveyed at exactly the same age. That way we can replicate findings across cohorts. Also, with our cohort 4, we can keep our study current. A lot of problems with longitudinal studies is by the time that they've finished, they're out of date. With our cohort 4, we can keep ourselves up to date. Also, with the different cohorts, we can assess the effects of history. For example, we can ask the question, what difference does it make growing up being gifted in 1970 versus 1990? The times are very different. What kind of impact does that have on development? And finally, as I mentioned before, our cohort 5 allows us to assess generalizability. To date, what we have already collected in terms of data is that we have data on these individuals at age 13, 18, 23, and this fall we are mailing out our 20-year follow-up survey to these individuals when they're at age 33, starting with cohort 1. Now, finally, before I get on to my data of my talk, let me just provide you the theoretical rationale or the background for our work. Now, our work is based on a well-known model of vocational adjustment that is called the theory of work adjustment that was developed by Renee Drawes and Lloyd Loftwith at the University of Minnesota over the past 30 years. The one attractive feature of this model is that it's readily extended to choice of college major and choice of a career. The general thesis behind the theory of work adjustment is that to assure vocational adjustment, we need a good environment-person fit. That is, certain environments need certain people. Certain people find certain environments rewarding. To create a match between the environment and the person in order to ensure vocational satisfaction, what these individuals have done is to look and break down the individual into 2 parts and also the environment into 2 parts. And we can look at the individual in terms of the abilities that they have or the skills that they can bring to a job, as well as their preferences and what are the types of things that they find reinforcing. What is the type of content that they like to work with? Similarly, you can break down the environment and you can look at the environment in terms of what are the ability requirements or the skill requirements that that job needs or requires. Also, what are the kinds of reinforcers that that environment can provide to the individual? In order to develop an optimal work environment, what you need is to develop correspondence between the individual's abilities and the ability requirements of the job. If the abilities of the individual and the ability requirements of the job match, you develop satisfactoriness. If the person's preferences for certain types of reinforcers the environment provides, you also have correspondence, which is called satisfaction. If you have satisfactoriness and satisfaction, you are likely to remain in a career and become vocationally adjusted. So what vocational counselors do in terms of working with their clients to help them find good jobs for them or good career choices is that they assess individuals' abilities and preferences. Now, how do we assess these abilities and preferences? How do we conceptualize abilities? There's a lot of debate going on about that, but a pretty well accepted representation of abilities is the Radex. And here, if you look at the Radex, what you can see is that you can look at abilities and they can be grouped into 3 content areas: verbal, spatial, and numerical. Also, within those content areas, there are different degrees of sophistication. And the closer you are to the core, the more abstract, the more higher level the thinking or the skills required. And so, for example, for the physical sciences, which is an area that I especially focus upon, the skills that are especially required in those disciplines are numerical skills and spatial mathematical, and they need to be very, very close to the core. Verbal skills are still very important, but could be moved away a little bit further from the core. But it's absolutely critical for a physical scientist to have skills that are very highly developed and at the most exceptional levels. Now, what about preferences? How do we assess preferences? Well, one way to look at preferences is the Hollenstein. And basically what he has done is to classify interests into 6 groups. And that they are investigative, artistic, social, enterprising, conventional, and realistic. So there are 6 types of individuals or interests. Another way to look at preferences is the study of values. And basically the study of values looks at preferences by breaking it down into 6 value types, and they are theoretical, aesthetic, social, economic, religious, and political. There's a lot of overlap between the study of values and the Holland's hexagon. Now, in terms of the physical sciences, what are the types of preferences that the physical sciences can reinforce? Basically, what we find is that individuals who go into the physical sciences tend to have very high theoretical scores. That is, they like to work with scientific ideas, philosophical ideas. They also have very high investigative and realistic interests. Also, people who are very high on the social side, that is, people who have very strong need for people contact, are not as readily satisfied by the physical sciences environments. Thus, to kind of sum it up, the physical sciences needs individuals with high math and spatial abilities, and the physical sciences are rewarding to individuals with high theoretical, investigative, or realistic interests or preferences. All right, that's enough of a background. Let's just get into the talk. But hopefully you can keep this in mind as I kind of start now going through the data. Basically, the first thing we identified and we looked at was to see, of these mathematically talented students, these thousands of students that we're tracking throughout their adult lives, and we're tracking 5,000 of them actually. We're working our way up to 6,000. Anyway, we're tracking them through their adult lives. And the very first thing that we found out was that these mathematically talented students enter the math sciences in 10 times the national rate. That is, when you think of our future pool of math and scientists, they're going to be comprised of individuals who could have been identified as mathematically talented at age 13. Thus, in terms of looking at gender differences along the math science pipeline and so on, it's very appropriate to look among the mathematically talented because that's the most likely group to be in the math sciences later on. Now, within the mathematically talented students, are there students who will gravitate towards the sciences, and are there students who will gravitate away to other areas? And are there gender differences along those factors? That's the rest of my talk. Well, let's first look at mathematical ability. And I guess the the article that kind of threw me into the doghouse with the women's movement in the 1980s. Basically, to go back to the talent search, in 1972, when we conducted our very first talent search, we were very surprised to find a gender difference on the SAT math scores. We weren't expecting it, and when we saw it, we thought it was just purely an artifact. But it wasn't an artifact, and in every single talent search that we've conducted since that time, involving over 1 million students, there has been a gender difference on the SAT math. And here, let me just kind of show you what the extent of that gender difference is. Here we have a score of SAT verbal score. Here we have a distribution of SAT verbal scores. And as you can see, for the boys and girls participating in our talent search at age 12, 13, there are no gender differences in SAT verbal scores. Here's the score distribution of SAT math scores. Now here you see quite a different picture. And here what you can see is that the distribution of scores for males is negatively skewed. And also you can see that the males are much more variable. As a matter of fact, if you could superimpose the distribution of female scores on top of the SAT verbal distributions, they would be indistinguishable. What we have here is that the male distributions are very different from what you, at least as a psychologist, would expect to find. We always think everything is going to be normally distributed. And here you can see that's not the case. And you can see that the boys are here. So what kind of gender differences does this kind of score distribution create? At the mean, it's about 0.4 standard deviations. But that's not the interesting part of this data at all. The interesting part of this data are the ratios at the tip, at the high end of the scale. If you look at the average score of our 7th grade males, which is 421, what you find at the average is that there are 1.5 males for every female. If you look at the average score for a college-bound 12th grade male, which is 500, you find 2 males for every female scoring that highly. If you look at the score of 600, which is the 83rd percentile of college-bound senior males, you have 4 boys for every girl who scores that highly. And finally, when you look at that elite level of scoring of 700 to 800 on SATM before age 13, we have 13 boys for every girl scoring that highly. These ratios have been stable for the last 20 years. They have not been changing. We have found them in Germany as well as in China. But the gender differences among the gifted in mathematical reasoning ability are also accompanied by gender differences in spatial and mechanical comprehension abilities. So this is not the only difference that we're dealing with when we look at gender differences in abilities. If you look at this slide here, which might be hard to read, here what we have are data of individuals in our cohort 4. So these are the Iowa students participating in our SciTag program. And we have data on these individuals obtained over 4 years. And what you can see, if you're close enough, you can see is that the data for all of these years continually replicate. And what we find here is that, again, here's the gender difference on the SAT math scores. No gender difference to speak of on the SAT verbal score. On the advanced Ravens, which is supposed to be a non-verbal measure, sometimes people say the nice measure of general intelligence, there are no gender differences. But if you look at spatial ability, 3-dimensional rotation only, that's the only spatial ability that shows a gender difference. But if you look at that, you'll see that there are quite some large gender differences there. And also mechanical comprehension. And although I don't have data for 1992 on here, because we only had one box filled in, I did run the data from 1992, and the gender difference again replicates. And for 1992, it's 0.8 standard deviations. It's a gender difference on mechanical comprehension test. So what we have here then is that among the mathematically talented, among individuals who are at least in the top 1%, is that we have gender differences in mathematical reasoning ability that are compounded by gender differences in spatial and mechanical comprehension abilities. So if you think of that theory of work adjustment and you think about the ability requirements of the physical sciences, in terms of the critical abilities needed for success in the physical sciences, we have gender differences in all of them. And they're quite large. And they've been stable for 20 years. Interestingly, if you look at these kids when they get to end of high school or end of college and you look at their achievement test scores in math and science, what we find is that even though those boys and girls have taken the exact same courses throughout their high school years, we find gender differences in achievement. Somehow, the boys have retained or acquired more knowledge than the females, for whatever reasons. Now, we've looked at abilities, but that's only part of the picture. What about values or preferences? Are there differences there that can make the disparities among the abilities perhaps even worse? And what we find, if you go back and look at this slide here again, is if you look at the theoretical score, you look at it here and you look at the boys versus the girls, what we find is that the boys have very peaked theoretical scores. That is, they are primarily theoretically oriented. The girls, however, are more evenly distributed along theoretical, aesthetic, or social. So again, what we find here is that the boys, what I would prefer to say, is that the boys are much more narrowly focused and the girls are more broadly focused. Now what about the other way of looking at values and preferences, the Hollins theme? Well, here's for another group of mathematically gifted students. And here what you see again is a difference pattern of preferences, preference profiles. And you can see again that the boys are peaked on investigative, while the girls have just as high investigative interests, but they have other competing interests of very equal value. Like look at, for example, the females' artistic scores. So again, what we find here are that the girls are more broadly developed and the boys are more focused. And indeed, that's what we find in terms of looking at how these students enroll in our courses during the summer. We find that 83% of our boys will enroll in either a math or a science course, and 50% of the girls will. What we say is that the girls don't like the sciences any less than the boys do, they just have other competing interests. And what basically, in terms of if you think about the math-science pipeline and what the implications are for this, is when we select students for undergraduate school and graduate school, we tend to select them on their math and verbal reasoning abilities. So there the girls are somewhat at a disadvantage. But compounding that is self-selection. And what we find is that individuals self-select in or out of the sciences based on their ability and value profiles. And so more of the females will self-select out of the sciences. They will choose other careers that is more congruent with their interest and value profiles. Before I actually show you what the implications of this data are down the road, let me just show you one more factor that works on the females' choices. And that is preferences for full-time employment by mathematically precocious individuals. Here we have individuals on cohort 1, 2, and 3. So you almost have here 20 years worth of students. And what we ask them is, what is your preference for continuous full-time work? And as you can see, essentially all the males say that they are going to work full-time until retirement. But only 50% or so of the females are. And this hasn't been changing over the last 20 years. Surely, this type of planning must have an impact on the kind of career decisions that they make. Okay, well, up to this point, what I have done is describe the students at age 13. Now, the critical question is, does this have any bearing or relationship to educational and vocational outcomes? All right. Again, to kind of remind you, what I'm going to be presenting now is data on these cohorts Here you have again what the cohorts are. I'm going to first present to you the data for cohort 1, then I'm going to go on and present data for cohort 2, and finally data from cohort 3. Now keep in mind as you look at these different groups and look at the decisions that they make at age 23, keep in mind that as we go down, we get more and more able. So this is top 1%, top half percent, top 1 in 10,000. Okay. So what are the career decisions that these kids make at age 23? So what we've done here is that we have individuals in terms of their career aspirations, whether they're going to have a bachelor's degree only, less than a doctorate, that no further, or doctorate or more. And here you have it broken down by the various types of majors and disciplines. Now if you look at this slide, there are several trends that you can look at. You can see that there are many more males who are choosing to enter careers in the math sciences. You can also look at that slide and you can see that the males are especially likely to be found in the more quantitatively oriented sciences. Males also have higher educational aspirations, and that the gender differences get larger with higher the educational level. Such that if you look at this box right here, what you find is, and we have that less than 1% of the top 1% females in mathematical ability, less than 1% at age 23 will be pursuing doctorates in mathematics, engineering, or the physical sciences. Less than 1% of the top 1%. That's pretty astounding. At least I think so. 8 times as many males are doing so. All right, that's cohort 1 that we identified in the early 1970s. What about cohort 2? Now remember, cohort 2 is a much more select group, so you probably would expect to find them more highly represented in the sciences. And indeed we do. But again, if you look at that table and study it, the exact same patterns that we found for cohort 1 is now found for another cohort of gifted students identified 5 years later on the average. Again, gender differences in science participation. Males are again clustered in the more quantitative oriented careers. Again, the gender differences get larger with each educational level. Now then, what about cohort 3? Now remember, what we have here are individuals who before age 13 scored at least 700 on SAT Math, or at least 630 on SAT Verbal. Those two scores have the same percentile rank. And some of those who scored both. Now all I have here is actually data for them at age 18. They haven't gotten old enough yet. We're just surveying them right now at age 23, so that data isn't in yet. But the data that we have for them at age 18, again, what you can see here is, first of all, you can see how few females we have. We have 157 males who are 700 down versus 17 females. Now some of you guys say, well, gee, Camilla, why did you quit so early? Well, it took us 5 years to get that many females. It just takes us a very long time. Actually, we had a few more than that, but they get lost in the other groups. Anyway, what you can see here is that even among students, among females and males in the top 1 in 10,000 in mathematical ability, you still find the gender differences in career choices. Now some of you, since we're all here in academia, the next question that you might think about is, well, how many of these kids, they're not kids anymore, but how many of these individuals are planning to go on for careers in academia, and is there a gender difference? And what we find is that there's twice as many males than females who plan to go on for careers in academia, university teaching or research broadly defined. So again, a gender difference. And so females are just not choosing those same type of tracks. Now the critical question is, at this point, is that among these mathematically talented students, can we predict at age 13, using our variables, can we predict who's going to be here versus who's going to be here? And so again, just to remind you about our model, and that the basic things that we're looking for is abilities and values and preferences. So we have followed up these kids, and we studied everything, not everything they did, but we studied a lot of things they did, and the kids think we studied everything. They get so tired of filling out our questionnaires. But anyway, we looked at family background, we looked at high school course taking, college course taking, self-concepts. We really tried to profile these kids very extensively. And of course, we looked at abilities and preferences to see what are the factors that we could separate, that could separate these two groups, those in the math sciences and those outside of it. And there were two factors that did the best job. That is, there were differences. Those kids in the math sciences were more mathematically able, and also in the other specific abilities. But most importantly, and the biggest difference of all, was in values. And that is, if you take a theoretical score and you subtract away the social from it, so you in a way have set up a dimension of people versus things. So you take theoretical minus social. That is the very best predictor of whether you'll be in the math sciences 10 years later. Also, there were differences in investigative and realistic. So yes, on this data, what we can say is that we can predict with very good accuracy among these top 1% kids who is likely to be in the math sciences and who is not. And we have replicated these findings across several cohorts. Now at this point in time, you might be wondering, well, now that's a pretty special sample that they're dealing with here. How well does this generalize to the rest of us? So what we started this last spring, we started a retrospective study of individuals who are enrolled in the top math science departments in this country. And we surveyed almost 1,000 individuals, half females, half males. It was quite a job, let me tell you, to find those females. Anyway, we got the responses in, and now we're trying to see, do the findings that we have for this SMPY cohort replicate for this other group of students who clearly, by all definitions, must be considered mathematically or scientifically talented. They wouldn't be graduate students in the top math science departments if they were not. All right. First thing we did was to look at their values. And again, what we found is that the theoretical value is their predominant value. And again, you can look at those preference profiles, but you can see the gender differences that we found in our sample. And you can see that it goes exactly the way it went for the other groups of students. But clearly, here is the big. As a matter of fact, if you look at the literature, what we generally find is that physical scientists tend to be very high on theoretical, extremely low on religious, and low on social. That's just the way our math talented kids are, and that's just the way these graduate students are. What about their abilities? You got their GRE scores. You got their SAT scores too. And these are 7th grade scores, by the way. These are 12th grade scores, and so on. And we didn't select them because they were town search participants, but a lot of them were. Okay, if you look at the scores here, what we have here are cohort 2. This is the SMPY group. So what you want to look at for now, we'll get to this cohort 2 here, is cohort 5. You want to look at the red arrows. And you can look at their scores. On a GREQ, GRE verbal. Clearly, these scores, the averages are in the mid-700s. The mode on GRE Quant for these kids is the most frequent score is 800. That is the most frequent score for these kids in the top math science departments. And you can look at their SAT math scores. Now, the question for me was, the critical question for me was, at a time when these individuals were in 7th grade, the talent search concept was not as widely spread as it is now. Now, as I mentioned, we have 150,000 kids taking these tests. When they were in 7th grade, we didn't have that many kids. It wasn't all across the country. It was just isolated in certain states, and participation was relatively low. So, what we did was that we gave a very complete description of what is a talent search, how you qualify for it, and if you did qualify for it. So we asked the students, reading this one-page description, would you have qualified for the talent search? 93% said yes, they would have. They were actually individuals who had participated in our talent search. 15% of them had.